All right, so I'm just here to help you out a little bit with 1.7. I forget the exact title, but let's jump right in. I don't want to waste any of your time. It might have been a while since you've seen some of this stuff, so just recall we're kind of talking about sort of the precursor to the multiplication rule, and it looks like we're touching on some aspects of the fundamental counting principle. Um, and we'll talk about that as we go along. But sorry about the sirens. So Matthew rolls a number cube labeled with the numbers 1 through 6. So 1, 2, 3, 4, 5, 6. So for that first probability, we have 6 outcomes, right? So out of 6 outcomes, what is the probability that he rolls a 4? Well, 4. I'm so bad. I'm so sorry. Um, 4 is one of those outcomes, right? So 1 out of the 6. And we are going to multiply by the probability that he gets a heads, right? That he flips a heads. And if you remember looking at a coin, obviously you can either get heads or tails. And heads is simply 1 out of those 2 possibilities. Right, and so when we multiply, it's super easy. Watch, 1 times 1 is 1. 6 times 2 is 12, and our answer is 12. So just recall that these are independent events, and when we have independent events, we have what we call the multiplication rule, but it's really also the definition of what independent events are. This is like a mathematical definition. So suppose we have 2 events, A and B. What independent events allow us to do is they create a multiplicative situation. So we could say, oh, the probability of this compound event, A and B. Well, we can find the probability of that by saying the probability of A times the probability of B. So in this case, our probability A would be rolling a 4, of which there is a 1 in 6 chance, and flipping a head. So really, the probability of rolling a 4 and then flipping heads, we can just say that's the probability of 4 times the probability of heads. Right? So not too horrible, right? As long as you're familiar with your fractions and everything, this should be okay. So looking at number, I'm not going to just like give you all the answers, obviously, but I'll point you in the right direction. What is the probability of rolling a sum of 10? And I don't want you to get too freaked out when you read that. That's just how we read dice, right? So when you roll dice, right? Let's say if you land on a 1 and then you land on a 4. 1, 2, 3, 4. We don't say, ooh, I got 1 and 4. You say I got 5, right? So, what is the probability of rolling a sum of 10? Well, think about how many total possibilities are there, and then how many of those total are a sum of 10. Right? So all you really need to think about is, well, how many total possibilities are there, right? And that'll go in the denominator. And so this one, it is a compound event. Technically, you're rolling 2 dice, but it's hard to conceptualize because you kind of are thinking of it in terms of a simple event in a lot of ways. How many tens out of how many total, right? I should say over how many total. All right, so that should steer you in the right direction. I believe you'll have to simplify a fraction to get the right multiple choice. To start a board game, the player who rolls 2 6s gets to go first. What is the probability that a player will roll 2 number cubes and get 2 6s? Well, this is very simple, right? So let's do 1, 2, 3, 4, 5, 6. We'll do that twice because we are rolling 2 dice, yeah? Right? And just tell me, what is the probability of getting a 6 times the probability of getting a 6, right? So hopefully, again, that steers you in the right direction. In Sal's socks, well, that's a tongue twister. In Sal's sock drawer, there are 2 red, 2 blue, 2 yellow, 2 black, and 2 green socks. If he randomly picks one sock and then another, which fractions should Sal multiply to find the probability of choosing a pair of green socks? So notice that these are what we're gonna call dependent events. So dependent events are they're kind of situations where this is not true, right? That is to say that I don't know why I keep doing that. That is to say that they are not dependent, obviously. So this they are not multiplicative. We can't just say, ooh, A and B is A times B, right? No, that is not the case. They are not equal. But then that kind of makes it, that begs the question, well, what is it equal to, right? So think of it this way, can like read through it, kind of conceptualize it, right? How many total socks are there? Well, judging by the number of tens in the denominator, I'm guessing that there's it's going to be out of 10. But let's find out, right? 2, 2, 6. So 2, 4, 6, 8, and so there's 10 total socks, right? And then he's going to draw one. He's going to draw one green sock. So the probability, we're looking for the probability of green and then another green. However, remember that he doesn't put it back, right? One after another. That is to say that he didn't put it back, right? So he no longer has 10 socks in the drawer, right? He no longer has. He pulls one green out, and then he's going to pull out another. So now there's only 9 left. Right? So again, not trying to give you all the answers, but hopefully this steers you in the right direction, okay? A bag contains 2 red and 3 black. If Abby picks a marble without looking, returns it to the bag. Okay, so that's very good. So returning it to the bag, that means that these are independent, right? That means that they are independent, which is good. It's less work for us, right? We can kind of go robot mode, so to speak, and just kind of multiply without thinking. So again, think about, we're looking for the probability that both marbles are red, both. So we're pulling out 2 marbles. We're going to pull one out, we're going to put it back, and then we're going to pull out another one. And we're asking, what's the probability that we do that, and both times we pull it out that it's a red marble? Well, again, find the probability of a red marble, of pulling out a red marble, and then multiply it by the probability of pulling out a red marble. And again, think about how many total do we have? We have 2 red and 3 black. How many total is that? It's 5. Right? So 5 should be in your denominator there. It should be over 5 both times, right? Because we put it back. So we pull it the first time, we put it back, so now there's still 5. Still 5 in the denominator. Still 5 in the bag, right? Okay, let me keep going. Sorry, it's my recording software. I don't know, why does that keep happening? Go down. There we go. Sorry about that. So a regular deck of cards has 52 cards with 4 aces. Carl asked a friend to pick a card 3 times, replacing the card each time. Ooh, maybe he's doing a magic trick. So I can highlight better than that. Replacing the card each time. His friend picked 3 aces. So what is the probability of picking 3 aces? Well, since he replaced the card each time, we know that these are independent. Like I said, as soon as you see independent, you can go robot mode and just start multiplying, right? And this one's not even asking you for like a final answer. Like, it's just asking you, what would the multiplication problem be, right? What expression will give the probability of that event? So find the probability of drawing an ace, and then find the probability of drawing an ace, and then find the probability of drawing an ace. I'll give you a big hint. The denominator will not change because these events are independent. That's not the only reason they don't change, but you know. A bag contains 4 red, 3 yellow, 3 blue, and 2 white for a total of 12. Ooh, very useful. So I know 12 is going to pop up in a denominator near me. If Lucia randomly picks 2 marbles without putting the, ooh, very important information, without putting the first marble back. So that means that this is going to be dependent. So these ones, dependent, we always have to think a little bit harder. We have to say, okay, what's actually happening here? What is the probability that the first marble is red and the second is white? So I'll be a little bit more formal. I'll give you the actual, the quote-unquote formula, or I'll kind of use the formula of dependent events to frame this one out. So the probability, the first one is always easy because the first one, nothing changes, right? So you start off normal. Okay, let's find the probability of getting a red marble, right? So how many red over the total number, right? Over the total. And then we're going to multiply that by, and this is going to be a little bit weird, the probability of white. So the probability of getting a white marble, but we're assuming that we got a red one out first, right? So that little black bar, you can kind of think of that as saying like after, right? So the probability of drawing a white one after a red one has already been pulled out, okay? So it's kind of hard. So find the number of white here. And again, in the denominator, it's going to be, okay, well, what is the total? Think maybe total minus 1. Maybe that helps. Number 8, Elliot wrote a computer program. And I'm sorry, I know I'm moving kind of fast. Feel free to just, pause. Obviously, this is a video. So you can pause and move back, whatever. Generates a number from 2 to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. So out of 1, 2, 3, 4, 5, 6, 7, 8, 9, he's going to run it twice. What is the probability that the number generated both times is a prime number? Now, this is independent. It's not apparently so. It kind of comes a little bit from the statement of the problem somewhat. It randomly generates a number from 2 to 10. So that means that it's possible that the same number could get picked twice. It's possible that, how do you say? It's possible that, sorry, I just lost my train of thought. Things aren't being ruled out, right? We're not saying, oh, once you land on 2, you can't land on 2 again. That's not what this is saying. It's asking, well, what's the probability that we land on a prime number twice? So prime numbers are numbers that have exactly 2 divisors, 1 and themselves. So funny enough, 2 is actually a prime number. 1 is not a prime number. Kind of funny. But anyways, that's not important. So prime numbers are numbers with exactly 2 divisors, such as 2, 3, 5, 7, 11, 13, 17, and so on. So how many prime numbers do you have out of our total? And then again, multiply that by the number of prime numbers. Mr. Garcia, number 9. Mr. Garcia has 15 boys and 10 girls for a total of 25. So out of 25 students, this is a dependent problem. Okay, so these are dependent events. This is a dependent compound event. So he selects 2 students at random to demonstrate how they solve an assignment or a problem. What is the probability that both students are girls? Well, let me ask you a question. Out of 25 students, there's 10 girls, right? So that's the likelihood that the first student that he chooses is a girl. Sorry, I'm still getting over this cold. He has a 10 in 25 chance of picking a girl the first time. However, once that girl is up on the board, doing the problem, she obviously can't be chosen again, right? She's already been chosen. So think about these numbers. Something is going to happen. These numbers are going to change, all right? And again, I'll give you a hint. There's one less girl. Okay? Michael has 3 quarters, 2 dimes, and 3 nickels in his pocket. He randomly draws 2 coins from his pocket, one at a time, and they are both dimes. He says the probability of that occurring is 1 over 4, because 2 of the 8 coins are dimes. No, he's not. He's not correct. No. Come on, Mike. Get it together, buddy. He's not correct. He's correct in the sense that the first coin that he draws out of his pocket, that will be the odds of getting a dime. The probability of the first time. But for the second coin, that probability is going to change, right? Because once he pulls 1 dime out, right, there's no longer 2 dimes in his pocket. Now there's only 1 dime in his pocket. And there's no longer 8 total coins, right? There's only 7 total coins. So take that how you will. Give me a wonderful sentence, right, explaining exactly what's happening here. But other than that, hopefully this helps. Please let me know if you got any questions. And thanks for watching. I appreciate you. Oops. I meant to do that.